continuing our look at complex numbers and the geometrical representation. So now we're talking about functions, okay? But how do you represent a function? You see, normally we have a nice two-dimensional coordinate geometry plane. We input an x and we output a y, and we can plot that point. But now we need a four-dimensional number plane, because we're going to input an x and a y value for the input, because you've got a real and imaginary part, and it's going to output an x and a y value. So you're feeding in two values and getting out two values. How on earth can you draw this on a two-dimensional space? You can't. You need four-dimensional space. Now obviously in a three-dimensional world, we can't draw a four-dimensional space. So what we do is we have two Argand diagrams. One for the input, one for the output. So W is some function of Z. So we're going to input Z, and the output will be, well, I'll call it W, omega. And then we're asked to find the locus of, well, it might be omega, it might be Z, depending on the information they've given us. And they'll give us some sort of condition on either the omega or the Z so we can work it out. Basically, try and make whatever the condition is the subject. So whether it be omega or Z. And that'll should give us the link between the two Argand diagrams. Now, some things to look out for. If they tell us that omega is purely real, then the key there is, that means the imaginary part of omega must be 0, or we could say the argument is 0 or pi. So that's an idea for that situation. If it's purely imaginary, then it becomes, well, that tells me the real part is 0, or the argument is plus or minus pi on 2. This one here, if you see the argument of, and the way I've phrased it there is a linear function on a linear function. So by a linear function, I mean a function of z. So you might have z plus 2 on z minus 3 or something like that. It's got to be a linear function. Is equal to some angle. That will turn out to be an arc of a circle. It'll be a minor arc if that angle is greater than pi on 2. It'll be a major arc if that angle is less than pi on 2. And of course, if it's equal to pi on 2, it ends up being a semicircle. Right, so let's have a look at a few of these. So there's our function. It's w is equal to, this time it is a w. W is equal to z plus 2, and the condition is that the modulus of z is equal to 4. And I've got a funny feeling that's a typo. Yes, it is. That too. It should be z plus 2 over z. I think when I was typing it up from my notes, my 2 looks like my z looked like a 2, so I've typed in a 2 there. So the function should be z plus 2 over z. Okay. Now the condition is on z. So I'm going to try and rearrange this and make z the subject. So zw is z plus 2. Z outside of w minus 1 therefore is 2. So z is 2 on w minus 1. I can now create the locus because I know the modulus of z is equal to 4. So there's the link. I can now say, well, that means the modulus of 2 on w minus 1 is equal to 4. Now I can rearrange this to get in something I recognise, play around with that, and we get the modulus of w minus 1 is a half. I recognise what that is. So my output will also be a circle. The input is a circle on z equals 4. The output will be a circle. W minus 1 is equal to a half. However, has this one got some exclusions? What would cause problems here? If z was equal to 0, is 0, 0 on that circle? No, so we haven't got an issue. Okay, so all those points are good. Here's one of those ones I was talking about, purely real. So they're telling me that w is purely real. I could do it algebraically, which a lot of people tend to go for because we love our algebra. So all right, let's put it into x and y form so I can see what we're playing with. Realise the denominator, and I'm not going to bother expanding the whole of that out. Because all I'm interested in is the imaginary part. And further to that, if the imaginary part is equal to 0, so I don't really need to worry about the denominator either. Because if a number or a fraction is equal to 0, it's got to be the top of the fraction that's equal to 0. So now I just have to pull out the imaginary part from the top of the fraction. So that tells me minus x plus 1y plus x minus 1y is equal to 0. And playing around with that, we simply get y equals 0. Simply get y equals 0. So our locus is y equals 0, but this time we do have to exclude a point. Because go back to the original question, w is z plus 1 on z minus 1, so z can't equal 1. And 1, 0 would be on the line, y equals 0. So we have to exclude that one. Bottom of the fraction can't equal 0. Now, to do it geometrically, and that's using the idea that the argument is either going to be 0 or pi. Okay, so the argument of z plus 1 on z minus 1 is 0 or pi. So the difference, if I was to get z, join it up to -1, and also join it up into 1. The difference between the arguments of those two vectors is either 0 or pi. So they either have the same argument or they're in opposite directions. Got to have a straight line. It's the only possible way. So let's just draw a picture. So there's 1 minus 1. There is there's a situation where the difference between them would be pi, going in opposite directions. Inside. Now, place z anywhere. 0, yes. Sorry. Because if you were to place it on the outside here and join them up, they would be going in the same direction. In between, they would be going in opposite directions if you were to place the z there. But we said with rays, we exclude the starting point. I've ended up with 2 points of exclusion. So how do I rationalise this out? So we've ended up excluding both plus or minus 1. Always go back to what the original question said. Remember, I've changed the original question to make it something simpler so I can solve it. But just like, we should be doing for any equation or anything, and I know we get lazy and don't do it, but theoretically we should always be checking our answer, going back to the original question and making sure it solves that. So if we go back to the original question, then we would pick up the exclusion of 1, 0, because again, can't have 0 on the bottom of a fraction. If I sub in -1 though, I get w is 0, and 0 is a real number, so it's fine. The argument of z on z minus 4 is pi on 6. So this is one of the ones where I've got a linear function on a linear function equal to some angle. So I know this is going to be the arc of a circle. All right. To help me, I'm going to split that up. Because what we're saying is, get z, join it up to 0, join it up to 4. The difference in the arguments will always be pi on 6, no matter where you put z. This is why you get a circle, because angles in the same segment are always equal. So it doesn't matter where you put z, you're always going to come up with the same angle. Okay. So there's 0 and there's 4. Now, the interesting thing here is, normally, I guess the natural thing to do would be to put z above the axis. And you'll notice I put it below the axis. There's y. If the argument of z minus the argument of z minus 4 is equal to pi on 6, then the argument of z must be a bigger number to get a positive. Well, if I was to put it in where, let's get a pen here, where automatically you would just sort of do it. So there's 0, what number was it? 4. Let's put it there. There's z, let's just call that one alpha, and that one beta. Which one's the bigger angle?
Beta.
Right. But hang on, we want alpha to be the bigger angle. So above axis is not going to work. Below the axis will work because we're dealing with negative numbers. So the smaller number being negative, subtract a negative bigger number will get you back into the positives. So that's how you can check. All right. I know it's a circle or part of a circle. The line joining 0 and 4 must be a chord on that circle. Now I'm going to use another idea, because the thing we need to find to find our circle, centre, radius. Okay. We know things like the radius will no, that's the wrong way of saying it. How do we say it? Perpendicular from the centre bisects the chord. Yeah, trust me, it's right. Okay. Yeah, I got a degree. So that's why I found the midpoint of the chord. Now, that means my centre will be there. Again, it's going to be below. Now, why do I know it's below? Remember, the angle is pi on 6, so I'm dealing with a major or minor arc? Major. Right. So if it's a major arc, then the centre must be on that side of the chord. If it was a minor arc I was finding, then I know the centre would be on the other side. Okay. We need to find the y value. Can we do it yet? Another bit of circle geometry. Angle at the centre is twice the angle at the circumference. We know the angle at the circumference is pi on 6. Therefore, the angle at the centre, pi on 3. But I just want this right angle triangle here. And that will be, symmetrical. So actually, there's the radius. I can find that. But that angle in there will be the same as the one between them, because I'm halving. Okay, so y over 2, I'm not worried about the negative at this stage. Y over 2 will be 10 of 60. So I know the y coordinate won't be 2 root 3, because it's below, but it'll be negative 2 root 3. So there's my centre. The radius, bit of Pythagoras, we can now work out the radius. Turns out to be 4. Okay. Ah, look at that solution. Isn't that a beauty? It's the locus of a major arc of a circle, x minus 2 squared plus y plus 2 root 3 squared equals 16, formed by the chord joining 0, 0 and 4, 0, but not including those points. Again, go back to the original question. Sub in 4, you get 0 on the bottom of the fraction. No good, can't have that. Sub in 0, you get the argument of 0. What's the argument of 0? You don't have one, because you haven't headed off in any direction yet. So you can't have 0. Another way you could write that is it's the major arc of the circle, x minus 2 squared, da 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 da, where y is less than 0. You could do that. Not quite as fancy, but it says the same thing. So what have we got to do? Some questions from 1F, just a couple of questions from Patel, but I've also run off from some of the past, just the geometrical ones, not all complex number questions, but just these geometrical ones going back.